In this video, we're going to look at the integral test. Let's look at the motivation. Consider summation n equals 1 to infinity 1 over n squared. Let's expand out this series. Put n equals 1, we get 1 over 1 squared, n equals 2, 1 over 2 squared as a second term, n equals 3, 1 over 3 squared, and so on. The question is, does the above series summation n equals 1 to infinity 1 over n squared converge? Consider the corresponding function f of x is equal to 1 over x squared. Now let's find the integral from 1 to infinity 1 over x squared dx. This is an improper integral, so we take the limit as b approaches infinity, integral from 1 to b, x to the minus 2 dx. Let's apply the reverse of the power rule, so we get limit as b approaches infinity, x to the minus 2 plus 1, we get x to the negative 1, divide by negative 1, that's the same as multiplying by negative 1. This is equal to limit as b approaches infinity, negative 1 over b, minus 1. This is equal to limit as b approaches infinity, 1 over b, negative 1 over b, plus 1. Now, as b approaches infinity, negative 1 over b approaches 0, so the answer is just 1. All right, let's look at the corresponding function y equals 1 over x squared, and let's look at the area under y equals 1 over x squared. Now, if you look at these rectangles, you will notice that these rectangles are actually the terms of the series summation 1 over n squared. So you can also tell that the area under the curve is larger than the area of the rectangles, and that's how we're going to prove convergence. So S is equal to the sum of the series is summation n equals 1 to infinity 1 over n squared. Let's expand out this series, so we get 1 plus 1 over 2 squared, that's 1 quarter, 1 over 3 squared, that's 1 over 9, 1 over 4 squared, that's 1 over 16, and so on. And you can see the sum of these terms of the series, 1 plus 1 quarter plus 1 ninth plus 1 16th, and so on, is exactly the sum of the areas of the rectangles under the curve. So S is equal to summation n equals 1 to infinity 1 over n squared. This is equal to 1 plus, this is less than 1 plus integral from 1 to infinity 1 over x squared dx. Now, it's very important that you see that the area under the curve, the improper integral from 1 to infinity 1 over x squared dx, is larger than the sum of these terms, 1 quarter plus 1 ninth, and so on, plus 1 16th plus 1 over 25, and so on. And this is equal to, we solved this improper integral in the last page, 1 plus 1 is equal to 2. So that's the motivation. The sum of the terms of this series corresponds to the sum of the areas of these rectangles, which is less than the area under the curve, and that's the motivation behind convergence. We're going to formalize it more. So since the areas of each of these rectangles is smaller than the corresponding area under the curve, y equals 1 over x squared, you can see on this page the area of these rectangles is less than the area under the curve. For this reason, S is equal to summation 1 over n squared, n equals 1 to infinity, is less than 1 plus integral 1 to infinity 1 over x squared dx. This is equal to 1 plus, and the value for this improper integral, we found it before, that's 1. 1 plus 1 is equal to 2. That means summation 1 over n squared converges because the area under the curve y equals 1 over x squared on 1 to infinity forms an upper bound for the series summation n equals 1 to infinity 1 over n squared, because the area under the function was larger than the areas of each of the rectangles that were actually terms of the series. And since the area under the curve is finite, since the integral converges, the series summation n equals 1 to infinity 1 over n squared also converges. So now let's talk about the integral test. Let's look at the formal definition of the integral test. Suppose that f of x is continuous, positive valued, and decreasing function on the interval 1 to infinity. then the series given by summation an is equal to, and summation n equals 1 to infinity f of n, is convergent if and only if the improper integral from 1 to infinity f of x dx is convergent. So part C, if the integral from 1 to infinity f of x dx converges, if the improper integral converges, then so does the series. The series summation n equals 1 to infinity an also converges. Alternatively, if the improper integral from 1 to infinity f of x dx diverges, then the summation n goes from 1 to infinity an also diverges. So basically it comes down to the integral. If the integral converges, the summation converges. If the integral diverges, the summation diverges. But of course, these conditions, continuous, these three conditions, continuous, positive valued, and decreasing, have to be satisfied before we can apply the integral test. The integral test cannot be applied if the function doesn't satisfy one of these conditions. All right, so some remarks. Number one, convergence or divergence of a series is not affected by adding or subtracting a finite number of terms to a series. So we don't need to start the series or the integral at n equals 1. So we can have n equals, say, 5 to infinity an, or we can integrate from 6 to infinity f of x dx. Number two, it is not necessary that the function f of x always be decreasing, but rather that f of x is ultimately or eventually decreasing for x larger than n. That means the function can do this. Initially it might increase, but eventually it has to be decreasing. Part 3, summation an, the sum of the series, the sum of this infinite series does not equal to the value of the improper integral from 1 to infinity f of x dx. The integral test does not give us the sum of the series. It only tells us whether the series converges or diverges. That's all it tells us. All right, let's apply the integral test to this question. Evaluate summation n equals 1 to infinity 1 over n squared plus 1 for convergence or divergence. Notice that the function f of x, the corresponding function 1 over x squared plus 1, is continuous, positive valued, and decreasing. On the interval 1 to infinity. Why is it decreasing? Because in the denominator we have a quadratic function, and in the numerator we have the constant 1. So definitely the ratio is going to decrease as x goes to infinity. All right, so we know we can apply the integral test. So we can apply, always check these conditions before applying the integral test. So we know we can apply the integral test. Okay, so we have integral from 1 to infinity 1 over x squared plus 1 dx. If this integral converges, the series will converge. All right, so this is an improper integral, so we take the limit as p approaches infinity, integral from 1 to p, 1 over x squared plus 1 dx. What is the antiderivative of 1 over x squared plus 1? What is the function whose derivative gives us 1 over x squared plus 1? That function is arctangent x. So limit as p approaches infinity, tan minus 1x, evaluated from 1 to p. So this is equal to limit as p approaches infinity, apply the fundamental theorem of calculus, put the upper limit in, we get tan minus 1 of p minus tangent minus 1 of 1. Now, what is arctangent of infinity? Because we're basically putting infinity in. We're taking the limit as p approaches infinity of arctangent of p. Arctangent of infinity approaches pi over 2. Because tangent of at pi over 2, the tan x function has a vertical asymptote at x equals pi over 2. What is arctangent of 1? What is the angle whose tangent is 1? That's clearly 45 degrees or pi over 4. Pi over 2 minus pi over 4 is equal to pi over 4. So we know that the integral, we have proven that the integral 1 to infinity, 1 over x squared plus 1 dx converges. This last statement, we must always state this at the end. by the integral test, the series summation n equals 1 to infinity 1 over n squared plus 1 also converges. So this is how the integral test works. First, you check the conditions, the function that has to be positive valued, continuous, and decreasing on the interval 1 to infinity. Then you form the integral, find the improper integral, and if the improper integral converges, then the corresponding series also converges. And alternatively, if you find that the integral diverges, the improper integral diverges, then the corresponding series diverges as well. In this case, the summation n equals 1 to infinity 1 over n squared plus 1 converges by the integral test. All right, thanks.